In this short video, I'm going to show you the solution to this problem number 19 from Giancoli, page 101. There are two parts to this problem. Part 1, where a person is falling from the roof of a house 2.8 meters high, and we're going to be calculating the velocity that that person reaches after falling 2.8 meters. And in the second part, we're going to be taking a look at the second part of the problem, where the person comes to rest after reaching that top velocity. We'll be looking at the force acting on the torso due to the legs. The first part of the problem can be treated as a free fall. The person starts at a position y0 equals 0 and a velocity of 0 and falls a distance of 2.8 meters. Since we don't have information about time, it's most sensible to use the v squared equals v0 squared plus 2ay minus y0 equation and solve that for the velocity of the person after they have fallen that distance of 2.8 meters. If you do that, you will find that the person reaches a speed of 7.4 meters per second once they have reached that distance. In this next step, we're going to use the same equation, but different initial and final conditions to find out what is the acceleration needed to stop an object moving at 7.4 meters per second after it moves through a distance of 0.7 meters. I find that this acceleration is 39.1 meters per second squared. And because the object is slowing down, the torso is slowing down as it falls, that acceleration is negative. It's important to realize that the negative 39.11 is the net acceleration due to the fact that there are several different forces acting on the torso. If you think about this, we have the force that is due to the weight of the object downward and countered by the force of the legs on the object upward. The net force acting on this is therefore going to be upward, having the net acceleration of 39.1. This problem specifically asks for us to figure out the force due to the legs. In order to do that, we need to calculate the weight and the net force and then create a net force equation and solve that for the force due to the legs. The net force acting on the torso is the force due to the legs upward minus the force of weight downward. Algebraically rearranging that net force equation to solve for the force on the torso due to the legs gives that the force on the torso due to the legs is equal to the net force plus the weight. So if we begin filling in the values that we know for this, we find that if we multiply the 42 kilogram mass of the torso times the 39.1 meter per second squared acceleration that we found in the earlier part of the problem, we add that to the 42 kilogram mass of the torso multiplied by the 9.8 meter per second squared acceleration due to gravity, that the whopping force of the torso on the torso due to the legs is about 2,000 newtons.